Okay, hi everyone. I'm here to talk about my first chapter of my PhD project, which is the cranial osteology of Metropolitan renwickae and the interrelationships of suspension-feeding pachycomiforms. So during today's talk, I'm just going to outline what pachycomiforms are and what their role was during the Mesozoic and why understanding them is so important. I'll then go through what data I collected, what my results were, and what implications my results have for the particular fossil that I looked at and for pachycomiforms as a whole. So pachycomiforms are generally considered to be early diverging stem teleos, which makes them part of one of the largest and most speciose clades of vertebrates that have ever existed. They are found generally between the Tithonian of the Lower Jurassic right up until the Maastrichtian of the Late Cretaceous. And whilst their distribution is generally considered to be kind of around Europe and North America, recent studies have found them as far away as Australia, South America, and even as far as Antarctica. So most fossils tend to be really well preserved. They're really cool. They're generally preserved in articulate 3D forms such as these. And so we know quite a lot about their morphology and how to identify them. The most famous example being the side-like pectoral fins, which is a really famous synapomorphy of pachycomiforms. However, despite all this information that we have, only a few studies have actually looked into their interrelationships. And any studies into teleos as a whole tends to use the one taxon as a kind of token basal teleos. So we actually haven't explored their interrelationships fully. And whilst most pachycomiforms are generally considered to be ecological precursors to pelagic predators such as tuna, the pachycomiforms that I'm looking at tend to be these giant suspension feeders, which is a separate clade here. Now these are precursors to suspension feeders such as baleen whales and basking sharks and whale sharks. There are 5 genera, which is Rhynchonyctis, Phaneryctis, Leadsichthys, Asthenocomus, and Martelichthys. And they're found from the mid-Jurassic, around the Colovian time, right up until the Maastrichtian. But unfortunately, we actually don't know too much about them because of their size and because of their reduced bony skeleton. We only have found fragmentary remains of a lot of the taxa that I've mentioned. So, for example, Leadsichthys is known from these really disarticulated fin rays, and Rhynchonyctis is only known from a few disarticulated skulls. However, that doesn't mean they're completely mysterious. Asthenocomus and Martelichthys have both been described from these really nice fossils. That picture is terrible, I'm really sorry. It looks better on my computer. And we have this really great information that we could use to find out more about these taxa, but no one has actually bothered to look. So the aims of my project is to redescribe the holotype skull of Metropolitan renwickae using micro-CT scanning. That means that we'll be able to hopefully improve our understanding of the internal and external morphology of Martelichthys itself, and then also use this new description to better understand the interrelationships, ecology, and evolution of suspension-feeding pachycomiforms. So this is Martelichthys. It's a really beautifully preserved fossil, and despite being really, really flat, it's probably one of the best preserved suspension-feeding pachycomiform skulls because all of its bones are preserved almost entirely in situ. This fossil was from the Colovian Oxford clay of Peterborough and has been described once already in a paper from about 2008, but that only described the external structures, and we wanted to use the internal structures in order to inform our phylogeny too. So for that we used CT scanning, which I did at Natural History Museum. And as you can see from the bottom picture, that's the kind of like internal view. So the fossil is incredibly flat, but it's also really big. So we had to scan it in 2 halves, which is why we've got this kind of like slight discrepancy here in the scan data, which made life pretty difficult. Because then I had to import all the scans into software called Mimics. That meant that I could go through, scan, and create 3D models of all the bones present using the scan data. I then imported that scan into a software called Blender, which allowed me to isolate the bones, look at them in different angles, and describe them accurately without them being obscured. So just as kind of an idea of what I made, this is my result. It's probably one of the kind of like cleanest that I could get from the scan data because it was really quite difficult to get through the kind of discrepancy in the scan. But we've got a massive amount of information compared to what the external description managed to give us. So for example, we managed to get details about the brain case, which is quite rare because the brain case tends to be endoskeletal and therefore doesn't mineralize during preservation. We also got a great amount of information from things like the hyoid arch, which you can see at the top right, which you might not be able to see, but there are sensory canals along there. That means that we can see where nerves and blood vessels went, which is something unprecedented in a lot of internal scans. So then we can start to ask questions about the phylogeny of Martolictis and maybe use it to confirm our current understanding of the placement of Martolictis as an edentulous pachycomiform. So we didn't do a formal analysis for this because we just simply didn't have enough data, but we did manage to look for a few kind of clues that might confirm what we already know. So, for example, we already know from previous description that Martolictis has those side-like pectoral fins that I mentioned before. We also have a couple of other pachycomiform synapomorphies, which is that they have a very reduced coronoid process compared to Watsonulus, which is our actinopterygian outgroup. And we also have this, the supraorbital doesn't form the dorsal border of the orbit, the dermis phenotic does instead. We then have a couple of things that can confirm that Martolictis is indeed one of the edentulous pachycomiforms. So aside from the obvious of not having any teeth, we also have this very broad parasphenoid, which makes part of the brain case compared to Pachycomus, which is one of the predatory pachycomiforms. But the most interesting thing that we managed to find is that they have these really interesting gill rakers compared to Pachycomus and other predatory pachycomiforms. They're much, much longer and have these needle-like raker teeth, which can help facilitate their ecology. So these gill rakers are really interesting because they are found in other suspension feeders that are extinct, such as basking sharks. And it basically means that they can catch microscopic particles and pass them into the mouth. This means that we can confirm from this evidence that Martolictis was indeed a suspension feeder. Oh, one of my things is missing. Sorry. What's more interesting is that the morphology of the gill rakers in Martolictis are completely different from those described in Leadsictis, which is another one of the edentulous pachycomiforms. Leadsictis has these really fine gill rakers called fimbriations, and Martolictis has these quite bulky needle-like teeth. So hopefully this means that we've got some kind of variation that can help us resolve this polytomy up here that has not yet been resolved. There are also a few other things that we can now use to kind of see the trends in ecology and evolution of Martolictis and the other suspension-feeding pachycomiforms. So one thing that unites Rhynchonictis, Martolictis, and possibly Asthenocomus is this elongated but beta-pterygoid process, which sticks off the back of the brain case. We also have Asthenocomus and Martolictis possessing this extremely long ethmoid region, which is between the eyes and the snout, which is not seen in Rhynchonictis or Bonorictis. And we also have this very short higher mandibula relative to the length of the lower jaw. Now, this particular trait is actually quite informative of their ecology as well, because a long ethmoid region, for example, could increase the buccal cavity of the mouth, but a short higher mandibula is used to basically support the lower jaw and keep it kind of structured. So a short high mandibula probably wasn't going to support something like continuous ram feeding where the jaw has to be held open, but a long high mandibula would. We've also got a couple of things that we don't quite understand. So we've got these supraorbital canals which sit on the rostrodome ethmoid, which are seen in Martolictis and Bonorictis, but they aren't seen in other taxa. Now, whether that's because this simply hasn't been recorded in Rhynchonictis and Asthenocomus, or whether this is an apomorphy of Martolictis or Bonorictis, this is something we can now ask. We also have this gap between the frontals, which kind of looks a bit like a dorsal fontanelle, if any of you kind of know much about cranial anatomy. That's found in Bonorictis, Rhynchonictis, and Martolictis, but hasn't been described in Asthenocomus. And this could be, again, because it's simply not been recorded before and actually is present, or this could be truly absent, and therefore something that unites Martolictis, Rhynchonictis, and Bonorictis to the exclusion of Asthenocomus. What's more interesting is that we can now start to ask questions about the origin of suspension feeding in pachycomiforms. I mean, these are really small predatory fish that manage to get somehow really, really big and start eating really, really tiny things. And that's really interesting because that's something that we've seen also in suspension feeding chondrichthyans and baleen whales. And the clue could be Ondemia here, which has similar morphological characteristics to Martolictis and Asthenocomus, most notably being the long ethmoid region. So this could be a precursor to suspension feeding, and this would fit with the phylogeny as Undenia sits as a sister taxon to the suspension feeding clade. However, this long ethmoid region isn't seen in Rhynchonichthys and Bonerichthys, so we're not sure if this is actually going to kind of give us more information about the evolution of suspension feeding, or whether this is something that we can start to explore more. So, moving on from that, my next project is going to focus on this guy, which is Pachycormus. This is one of the most basal pachycormiforms, and it's one of the predatory taxa that I mentioned before. Now, this is generally the one that's used as a bit of a poster child for pachycormiforms. Whenever they're represented, people tend to use this guy because we know the most about him. However, it's unfortunately still quite poorly described. We still don't know much about their ecology or their evolution, despite the wealth of fossils we have available. We also only tend to have external analyses, whereas we would like to look at the internal anatomy, because as you can see, the internal structures can be just as informative phylogenetically. So my next project is going to work on that. I'll be using CT scanning again, and this is the result so far. And this is the information that I've managed to gather over the last few months. We've managed to get lots of information about the internal anatomy that would previously have gone unnoticed, such as the brain case, the gill skeleton, and those gill rakers that I mentioned before, and things like the pectoral girdle and the fin. And this means that we can now start to ask questions about the ecology and evolution of the predatory pachycormiforms and better understand the group as a whole. Thank you, and any questions?